Hey class, Sir DV here again. Let's continue on the tension member concepts, and we are going to start now digging into some computational aspect of how members subjected to pure axial tension is analyzed. Okay, so for the definition of tension members, they are just those members which includes those subjected in pure axial tension applied to the centroidal axis of the member, resulting to a tension stress at the cross section. Okay, so the point wherein the definition states that the member is applied, or the member is subject to a tensile load at the centroidal axis simply restricts your member behavior into a pure axial tension. Okay, so the passing of such force of tension, which is basically at this is now the centroidal axis, okay, of the member, is a restricting factor that makes your behavior purely in tension. Okay, so this is a pure axial tension, because later on when we try to mix up tension limit state into other limit state, we will be having some adjustment on the formula that we ought to consider. Okay, so the limit state condition for strength is now your tension. Okay, so this is now the limit state condition for what? This is the strength limit state. So for serviceability, we tackle it differently. Of course, strength has the ASD and the LRFD version. We will try to tackle each individual approach as we go along. So for the notation, I'd like you to familiarize yourself on the following variables or arguments as defined, and we will be familiarizing ourselves to this as we go along, again with the computation. But of course, the more important thing here is you know what E means, this effective, the jitter, the gross, the aider, the net. Okay, so we're talking here of the area variable. These are all area. So this is a property of the modulus of elasticity of steel, which is basically 200,000 megapascal, or 29,000 KSI. Okay, so if we are talking of the English units. And the FU/FY are the steel property, material property. G are hole spacing. Okay, so these are hole spacing for bolted connection. L is the member length, of course. T's and P's are forces. Okay, so we refer here to the force variable, in which your U becomes your factor, the combination. Okay, so the U depth, when you say TU and PU, these are factored load combinations. So whatever we discussed on our first lecture will actually be applied to this. While N means the nominal strength. Okay, factored and nominal. So the U, the capital U, on the other hand, is a reduction coefficient owing to the net area. So I'll explain to you this later. And the phi becomes the strength because you apply what you call a reduction coefficient phi, or resistance factor phi, for tension. And for ASD, you will be using omega for your factor of safety. So this is normally used in ASD, and these are normally used in LRFT. Okay, for the nominal strength requirement. So this is now when I ask you what is the requirement, the criteria or requirement. No? The word criteria or requirement for LRFD is concerned. This is now your criteria. Okay, so always what? Always the formula is R greater than Q. Okay, so your resistance is simply your design strength, your tensile strength, while your Q are the required strength given by the load combinations, the factored load combinations. And what did I tell you in our design philosophy? That the engineer will be identifying the limit state uh, condition that he believes is significant to whatever member he or she is designing. Okay, so in intention members, these are the significant limit state we ought to consider. The first one is the yielding of the cross section which is away from the connection. Okay, so what does this means? If we have here two parts, okay, so we have here a welded or let's say a bolted connection here. So this is now your member, which is subjected to a tensile force. So when we talk of the yielding of the gross section, we focus our concern on the failure beyond the connection, and this is the region in which your member is connected. So this is what you call the connection. Okay, and for the yielding, we have to be away from the connection. So we will now try to analyze, or we will analyze the yielding as far as this section is concerned. So this is now section AA that will give you the yielding. Okay, the yielding failure brought about by the application of the tensile force T without considering yet the connection. Okay, so we have to deal with the limit state one by one. And this is just a simple force times area. If I have, a stress times area. If I have here a stress, okay, a stress, I have an area. This is now your force. So my formula for the resistance will actually come from the yield stress or the yield strength multiplied by the area at the gross, because this is the gross section. Okay, so this is now your first limiting state for tension. And for the second limiting state, we now focus on the connection itself. So in the connection, you will notice the only difference between the two is the strength involved and the area involved. Okay, here we have the yield. Here we have uh, a rupture strength or the tensile strength. Okay, remember the stress strain curve. Okay, so yield, uh, plastic strain, and then hardening. Okay, so when you talk of your yield, you talk of this level Fy, and when you talk of the rupture, you talk of this ultimate or the tensile strength Fe. Okay, now also for the area, you're talking here of the gross. Here you're talking of the net. That's why this is AE. And to give you an additional information, this failure is actually ductile in a manner, and this is brittle in the manner, which means to say that when you have a ductile failure, your failure becomes more gradual, dahan-dahan, and this is abrupt or sudden. Okay, so imagine the bolt here becomes destroyed, or maybe the part of the steel here failed due to shear. Then this becomes a brittle failure. While at the cross section, there will still be necking, there will still be uh, a plastic strain hardening that may come into the picture prior to collapse. Okay, so this will be discussed separately when we talk of the effective area. But to give you the formula, the effective area is a function of the reduction factor, or the reduction in area multiplied by the net section, or the net area, sorry. And U is equivalent to 1 minus x over L less than 0.90. You just substitute there, you get this formula here, where x is the center of gravity to the plane of load transfer and L is the length of connection. So I'll be discussing this specifically on the sample problem. Okay, for the third limit state condition for strength, the block shear failure at the connection is um, another source of brittle failure. And there's some definition on what is the tension fracture limit and the shear fracture limit based on this formula, but I'd like to show you now the picture of what and where the shear fracture is happening and the tension fracture is happening. Okay, so the tension fracture is actually described in the area. So we're talking now here of this width or area, this part here, which is perpendicular to the tensile force. Okay, so this is a perpendicular, this is the tensile direction. So the force is here, the direction is horizontal, and the area we are considered that will manifest what you call a tension fracture failure is this one. Okay, so this will actually be what? Paired, no? Mapupunit ito. And since this is perpendicular to T, then this is a tension fracture. While on the other hand, the shear fracture are this one. Okay, so these are the shear fracture area. And the stresses here are shear stresses. Here, these are the tension stresses. And here, these are the shear stresses. Okay. So the shear stress now are parallel to the area. Okay, so T is parallel to the area for shear, while T is perpendicular to the area for tension. Okay, so that is the way how to deal with it. This means that this is parallel symbol, and this means this is perpendicular or 90 degrees. Okay. So we will be computing this area on the basis of the length of those part which are teared and sheared multiplied by the thickness. Okay, so I will explain to you that later. And also the formula here are actually empirical formulas that gives you the limiting value upon which this resistance or strength were derived. Okay. Okay. So I won't dig into the to the derivation yet. It will just confuse you, but I'd like you to take note of what I emphasize. Okay, note 1, the additional nomenclature, A and V. Okay, V is shear, N is net, V shear, G is gross. So you call this now the net shear area, the gross shear area. Okay, N is net, T is tension, G is gross, T is tension. So you call this now the net and the gross tension area. So you just look into the nomenclature. I took a picture of what, not, I didn't took a picture. I just get a photo of how the tension fracture and the shear fracture happens, no, in actual situations. So note 2 here, that the factor of 0.60 for Fu or Fy is based on the von Mises yield criterion, which is exactly equivalent to 0.577 rounded into 0.60. Okay, so on the next video, I will be discussing to you the von Mises yield criterion as one of the most commonly used failure concept and failure theory in failure mechanics. Okay, so that's it for the limit strength or limit state conditions as discussed. So I'll see you on the next video to discuss to you the von Mises yield criterion. Thank you very much.